Hello, we are starting topic 2 of the introduction to digital system design. And we are doing number systems. Everything in a computer system, in a digital component, is binary. And therefore, we need to familiarize ourselves with binary system in order to be able to process components of a digital system. Okay? And so the focus is binary, even though there are other bases of numbers, base 7, base 5, base 6, whatever there are. But then our focus is only base 2. Okay, and then we will be showing binary system. We talk about Y binary. We will be talking about decimal to binary, binary to decimal conversions. Where we will be talking about hexadecimal and octal. I just said that we only do binary, but then I'm talking about hex and octal, which is base 16 and base 8. So why do we do this? We will, when we get to that, we will be discussing the reason for doing hex and octal. And then we'll be doing coding systems. Coding system meaning that not everything in a digital system is necessarily number. Okay. Other representations based on binary are also possible. And then doing all of this, we will get into the binary arithmetic. When we are dealing with a computer system, a component, a digital component, we cannot just put words inside the processor. We cannot just write whatever we are writing that is comprehensible to you and I. We cannot do that for the computer. We have to represent it in the computer language. And computer language, when it gets down to it, it's only binary. Everything is represented in binary, 1 and 0. Okay? What's the reason for this? The reason for this is that, as we have discussed already, down inside, when you look at a very complex system, when it comes down to the actual hardware, that actual hardware is a transistor. And this transistor behaves in a switch fashion, meaning it's on or off, because the base of all digital system is a transistor. And transistors behave as switch on and off, two states. Therefore, everything in a computer system is based on that two-state system, and therefore is based on 0 and 1. And therefore, everything must be represented in the form of binary. And that's the reason for it. If I had switches that would be working in 3 states, then perhaps everything would be trinary. Okay, but then right now I have 0 and 1 as the actual values that I will be using, and therefore I have to learn a little bit about binary system and how they represent numbers, how they represent text, how they represent words, and on and on. Okay, so in the lowest level, which we have already discussed, computers work with 0 and 1, a transistor. Okay, these are 2 transistors that we'll be discussing. Let me do a little bit better drawing this. Okay, these are 2 transistors that we'll be discussing later, and they work exactly like a switch. The one on the left hand side, if there is a 1 on the gate input of it. This one, it conducts. This one, if there is a 0, it conducts. Okay, so it either conducts or doesn't conduct. It either has a 0 or a 1, and everything is binary. Binary is base 2. Okay, and we work with base 10. Okay, we have 10 fingers. Okay, and therefore we have the decimal system. We can distinguish, or going back years and years, we can distinguish one of these 10. Okay, and therefore the base that we use is 10. Computers, on the other hand, only distinguish two things, on or off, and therefore they use base 2. All numbers we represent are decimal digits. So if we have a big number, we have several decimal digits because we have 10 fingers. The computer, though, it has only 2 distinguishing values, and therefore if it wants to represent a large number, it has to have many, many binary digits. If you look at the decimal number, we have, let's say 25.36. We have a decimal point. We have an integer part. We have a fractional part. The same thing with binary numbers. We have a binary point. We have a integer part, ones and zeros, and we have a fractional part, ones and zeros. Let's look at 25.13, which is a decimal number. Okay, and if I want to evaluate this decimal number, I say, well, on the left-hand side of the decimal point, the weight of the digits is 10 to the power of 0, then 10 to the power of 1, 2, 3, keeps going up. To the right of the decimal point, I have the weights are 10 to minus 1, 10 to minus 2, 10 to minus 3, and on and on. Okay? And therefore, 10 to minus 1, you multiply the digit by the corresponding weight, you multiply the digit by the corresponding weight, this, and then that becomes the value. Nothing surprising, if you multiply this and add them, you will come up with 25.13. We do exactly the same thing with binary numbers. Okay? So here, 25.13, this is the left-hand side, this is the right-hand side. Integer and the fractional part. Well, the same thing with the binary number. I have a binary point, not a decimal point. To the left of it, I have integer digits, and the weights are 2 to 0, 2 to 1, and then keep going to the left. There are, for the same exact number, there are definitely more binary digits than decimal digits. So if you take a decimal digit equivalent of it is turn it into an equivalent binary number, you will see that you have far more binary digits. To the right, I have the weights are 2 minus 1, 2 minus 2, and so on and on. In order to do this conversion, you conversion to decimal, what you do is you start at this point, and then again you go to the left, multiply all these digits by their corresponding weight, like for example this, multiplied by this, and on, and then you add all of these together. You add all of these together. What I have on the left-hand side, which is this. What I have on the left-hand side is the binary number, and then add them all up. You come up with the equivalent decimal number. Okay? So basically, this is the way you do the conversion. You take a decimal number, and for the integer part, which is this, For the integer part, you keep dividing by 2. Okay, so we have, let's say 29 is a decimal number, or let's say that we have 29.61. 29.61 I want to convert to binary. Okay, I put aside 61. I deal with the 29 first, and then keep dividing. Okay, fine. 29 divided by 2, I come up with 14. Let me use my highlighter. I come up with 14. The remainder is 1. The remainder obtained is the first digit closest to the binary point, and therefore this is this. What I come up with is 14. I divide again. Now I take 14. Now divided by 2 again, I come up with 7. The remainder is 0. Okay, that's next to the previous one, which was closest to the binary point. Now this is one step further. And then I take 7. Divided by 2 again, I come up with 3, and then the remainder is 1, and therefore this is this one. And then I take the result 3 divided by 2. The remainder is 1. The remainder is 1. This is this one over here. Okay, and the very last result is 1, which is, let's use yellow, this one here. Okay, when you can no longer keep dividing, then the result is this. Alternatively, you can do this. Alternatively, which is really easier for me, is, let me do it different way. You can say that the weight of each position is 1, 2, 4, 8, 16, 32, 64. Okay, these are the weights. Let me 64. And lost my yellow. I take 29, start from the left hand side. And can I subtract 64 from it? No, I cannot. Can I subtract 32 from it? No, I cannot. Can I subtract 16 from 29? Yes, I can. I end up with 13, and therefore I have a 1. Sorry. Then take 13. Can you subtract? Now, you're not dealing with 29 anymore. We are dealing with what is left. 13. Can I subtract 8 from it? Yes, I can. So I put a 1 here. I subtract 8 from it, and then I have 5. Can I subtract 4 from it? Yes, I can. Can I subtract, what I have is 1. Can I subtract 2 from it? No, I cannot. I put a 0. Can I subtract, well, 1. Then you put a 1 here. Okay? So either do the dividing like this, or take the number, start from the left-hand side, and the weights go like 1, 2, 4, 8, 16, 32, 64, 128, 256, 5, 12, 10, 24, and so on and on. Okay? And then start from the left-hand side. Keep putting zeros until you reach a number that you can subtract from. All right, that is for the integer part. You do the opposite for the fractional part, okay? For the fractional part, you keep multiplying by 2 instead of dividing by 2. Okay, so let's do this. 0.61 multiplied by 2 is 1.22. Drop the 1, not really drop the 1, use the 1 as the digit closest to the decimal digit. Sorry, closest to the binary point. Drop that and then multiply what is left by 2 again. So you have 1.22, take the 1, put it next to the binary point, and then use 22. Multiplied by 2, you come up with a 0.44. Take the 0, continue with 44. 44 multiplied by 2, you take the 0, and then you end up with 88. Take 8.88 multiplied by 2, take the 1, and then continue with 96. Multiply 96 by 2 is a 1, then you get 92. Multiply, you're probably wondering how far I want to go with this. I'll tell you in a second. Take 0.92, meaning just remove this 1, put it here, take 0.92 multiplied by 2, and then that's 1.84, then you put a 1 here. Okay, if you want to continue, you will do the same thing. That meaning that you multiply 0.84 by 2, which is a 1 here. Okay, I'm not going to do that. The rule is, as you are converting, as you are multiplying, in order to keep the same precision, every decimal digit translates to 3 binary digits. Okay, look, if I had 0.61 and a 0 here, that means I have 3 decimal digits. Since I have 3 decimal digits, I have to do 9 binary digits. But now that my number is 0.61 and no 0 here, that means I don't really care about the precision to the right of this. I only care about 2 decimal digits of precision. And therefore, I translate that to 3 binary digits, and therefore, I only go up to this. Again, if it was 0.610, I would do this 1, 0, 0, 1, 1, 1, 1, which is 84 times 2. This is 1.62. Then there will be another 1 here. 0.62, and then I think there would be a 0 here. Okay, so if it was 0.610, this would be the equivalent with the same precision. Now that I have 0.61, it will be 0.92. All right, putting the two parts together, meaning the previous one, slide 6, and putting this one together, the decimal part was 29, and the fractional part is, the decimal number was 29.61. The fractional part, now I have 11101100111. The same way that I said that you can take the number and keep subtracting weights from it, I can do the same thing here. Let's do this. On the right hand side of the decimal, on the right hand side of the binary digit, the weights go. See, before I had 220, 221. Here I have 22 minus 1, 0.5, 0.25, 0.125, 0.0625, 0.03125, 0.01625, I think. Okay? Now you have 0.61. Take 0.61 and subtract whatever you can from it. Can you subtract 0.5 from it? Yes, I can. And what I end up with, 0.61.5 subtracted from it, what I end up is 0.11. Can you take 0.25 from it? No, you cannot. Can you take 0.125 from it? No, you cannot. Can you take 0.0625 from it? Yes, you can. You subtract this, you subtract 0.0625 from it, and then you end up with something. I'm going to cheat from this point on and not do the arithmetic. And then what I have is I can subtract 0.03125 from it. I can subtract this from it. Okay? And therefore, this is another way of converting binary numbers to, or the decimal numbers to digital, to binary numbers. Everything is binary. Everything, absolutely, everything is binary. Okay? But then look at these numbers. I have, just look at this little example. This is a simple number. Then I have 29.61. Then it is 11101. And then on the right hand side, lots of ones and zeros. Representing this is very error prone. And then it takes a lot of space. Okay? So instead of representing these in binary, what I can do is turn it into hex or octal. Actually, hex is the way it goes now, but then octal was used many years ago. The thing about octal and hex, let's talk about hex now. The thing about hex is that, bring it on this side. The thing about hex is that every 4 binary bits fit exactly in one hex digit. 0, 0, 0, 0 binary is represented by a 0. 1, 0, 0, 1 is represented by 9. 1, 0, 1, 0 is represented by A. 1, 1, 1, 1 is represented by F. That means if I take 4 binary bits, okay, and replace them with a hex digit, they don't go across other 4 bits of the binary number. That means I can very easily partition a binary number starting from the fractional point, or from the binary point, to the right 4 bits at a time, to the left 4 bits at a time. Individually, independently convert them all into their hex equivalent. The only reason we use hex is that the conversion from hex to binary and from binary to hex is easy. And then hex takes a lot less space than binary. That's the only reason. Absolutely. The only reason we use hex is this. Hex is so close to binary. It's so easy to go back and forth between binary and hex that a lot of files with hex format, they even call them binary format. It's really not binary, but they refer to them as binary. Okay? So it's a more compact way of representing binary numbers. So let's look at this number. See, this is 35, and then with octal is the same way, except that instead of 4, we have 3. Okay? Word length for today's machines, or back when Intel 4040 was created in early 70s, word length was multiple of 4. 4-bit, 8-bit, 16, 34, 32, this and that. And therefore it's easily divisible by 4 hex than 3. But then since octal was used many years back, then we also talk a little bit about octal, and that is take 3 digits at a time instead of 4 digits at a time. So here I have the take the binary point, Go to the right of it, 333. Go to the left of it, 333. And then independently, individually convert them to their hex equivalent. For example, 100, okay? 100 is 4. 011 is 3. Okay? So here it is. 0, 0, 0, 0, 0, 1, 0, 0, 1, 1, 1, 0, 0, 0, 1. Okay? 1, 1, 1. That's it. So this is digit 0, 1, 2, 3, 4, 5. I missed one. 1, 0. Yeah. 1, 1, 0. 1, 1, 1. Okay? These are the octal digits. These are the octal digits. And then take every 3, convert them to their corresponding octal digits, like 100 is 4, 011 is 3, 010 is 2, and then 111 is 7, and that's all there is to it. And the same way with hex, you do start from the binary point to the right 4 at a time, to the left 4 at a time, and then you will be looking up into this table. So 1100, 1100, this is C. 0101, 0101 is 5. And then 0011 is 3. 0010 is 2. Okay? That's octal and hex conversion. And the opposite of it is also true. So if you have A 5.2325 and this is hex, you want to convert it to binary, you say A is 10105 5 is 0101. Okay, 2 is 0010, 5 is again 0101. Okay, if you had a D here, that would be continuing with 1101. Okay, take 4 at a time, do the conversion. Coding systems. We leave this for the next part.